Okay. Assalamu alaikum and good evening, everyone. Today we are going to start with question number 7. Okay. Sunset yellow is an additive used for coloring foods. A synthetic route for making sunset yellow. Okay. Molecules E and G each contains one SO3 negative group. See, here we have E, here we have G. These groups are unchanged in the formation of sunset yellow. Okay, that's fine. State the molecular formula of sunset yellow anion. Okay, so if you see, this is the whole molecule, right? And we have to write the molecular formula. So if you look at the carbons, let's start with carbon. So how many carbons we have? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we got 16 carbons. C16. Now let's talk about the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at these 10 places, we have a hydrogens. So C16, 10. Okay. And then if you see the number of nitrogens, we have 2 nitrogens. If you look at the oxygen, we have 7 oxygens. And then we have 2 sulfur, so S2. And as it's a negative ion, and if you see, there are 2 -1 charges. So it is going to be -2. Am I not audible to you, Shahriar? Okay. Now, in the next part, Walaikum Assalam, Hassan. Reduce the structure of E, F, and G and draw the in the boxes figure 7.1. Okay, let's start from here. So if you see, it's NH2. So if it's NH2 over here, so it means, and it's a C6H4. So basically C6H4 is a benzene ring. And here we got SO3 group. You can write it like this or like this, SO3 negative, and here we get NH2. Is this understandable to all of you? Now, if you look at it, C10H6, so basically it is this group. Because here you have a C10. So one benzene ring, second benzene ring. Here we got SO3 and here we got OH. Is this clear to all of you? Abdullah, it's easy because if it's NH2 group, so NH2 is the electron donating group. So it normally, substitute at 2, 4, and 6. And how could I identify these positions? Because with the help of this, if you look at this one, so this is a nitrogen and here we got the SO3. So they are exactly opposite to each other, the nitrogen and SO3. So it means that is these two are going to exactly opposite to each other. Is this clear, Abdullah? So basically, this came from this turns into this and then this. And this one is over here. Okay. Now, so here we are getting a N double bond N and an azo die. So it indicates me, or it helps me to identify that this phenylamine basically convert into diazonium ion. So here we get the whole thing stays the same. Only here we get nitrogen, triple bond nitrogen with a plus charge. Is this understandable to all of you? Now, when see these two reacts, so this nitrogen, if you see bonds with this one over here, you see, and we get this. Is this clear? Is this understandable to all of you? Okay. Now, in C, such as the suitable reagents and conditions for step 1 and 2. In step 1, if you see diazonium ion is formed, right? So, to produce a diazonium ion, we react nitrous acid. So you just write HNO2, or instead of HNO2, you would write NaNO2 plus HCl. And the temperature conditions would be temperature is equals to or less than 10 degrees Celsius. No, sorry. It's for the second step, I assume. No, sorry. Yeah, it is for this step when you have to make the diazonium ion, you have to keep the temperature below 10 degrees Celsius. Okay, now step 2. In step 2, this reaction occurs when the dye formed, the azo dye formed. This reaction is called coupling reaction, in which a diazonium gets substituted on the benzene ring to form a dye. And for this reaction, we need an alkaline condition only. Both the reactants are available. So, sodium hydroxide aqueous. Abdullah, it is because of this group. This group is electron donating, right? This is not electron deficient. Yes, this become electron deficient. So here on a benzene ring where the substitution is occurring, we look on the group which is bonded to that benzene. So if you see over here, this group is getting substituted on this part of a benzene. It is because of this OH group, because this OH is electron donating. Now, if some substitution occur on this benzene ring, then we will look into this group as it's electron deficient. So it is going to substitute at 3 or a 5 position with respect to it. Is this clear? Okay. Now D part. Predict the number of peaks in carbon-13 NMR spectrum of sunset yellow anion. Okay. So now number of peaks for carbon-13. So let's start using different colors to figure out. Let's suppose this one has a different environment, this one has a different environment, this one, and then these two. Then this one has a different environment, and this one has a different environment, and this one has a different environment. So how many right now till here, how many different we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got right now, no, not 12, 10. Again, count Abdullah. Now, if you see, these two are going to have a same environment, isn't it? In the same way. these two are going to have a same environment, but this one is going to be different and this one is going to be different. Now, if you count 10, 10 over here, 11, 12, 13, 14. So there are 14 different environments. Is this clear to all of you? Okay. Now question number 8. Capsaicin is found in chili peppers. Okay. You should assume that CH3O group is unreactive in the reactions involved in this question. Name all the functional groups in capsaicin in addition to the CH3O group. Okay. So if we talk about the CH3O group, in addition, so there is no need to put this one. OH group is bonded to a benzene ring, so it means it's a phenol. This one. Then C double bond O is bonded to NH, amide, and then C double bond C is an alkene. Is this clear? If any one of you has any confusion, you can ask. Now, complete the equation for the reactions of capsaicin with an excess of bromine in the dark. Okay, just give me a minute. Please, 1 minute. Okay, draw the structure of the organic product in the label box. Okay, so we are reacting it in the dark. Okay, so see what will happen. As see, we have a benzene ring, right? So, and on a benzene ring, we have a phenol. So on a second of phenol, one bromine gets substituted because of benzene, because of a phenol group, we don't need any halogen carrier. So the other bromine would form HBr from the bromine molecule. Now we have rest of this structure. And here we have a double bond. So on both the carbons, bromine gets bonded. Yes, H of a benzene ring in the phenol gets substituted, not this OH. This H is only substituted when we react it with sodium hydroxide. Please do go through the reactions, okay? Okay. Now, see. Capsaicin is heated with an excess of hydrogen gas in the presence of a platinum metal. Okay. The six-membered ring reacts in the same way as benzene. Under these conditions, draw the structure of the organic product. So see, excess of hydrogen gas in the platinum metal in this case, and it's a capsaicin. So what happens in this, and as they have give you the reference with the benzene ring. So in benzene ring, it will happen like this, that the pi system gets, disturbed, and all the pi bonds gets removed, and we got a hydrogen bonded to each carbon of the benzene ring. So it would be like this. And in this case, the rest of the structure remains same. This whole thing remains same. Only this pi system over here is actually uh, disappears because each carbon now gets one more hydrogen over here. And here there is a double bond. So on that double bond over here, the addition takes place. And we got a single bond over here. Is this clear? So this would be the structure in this case. Okay. Now D part. When capsaicin is treated with the reagent J, under suitable conditions, of the product is methyl propanoic acid. Okay. Identify reagent J. So we are getting a methyl propanoic acid. Okay. So we are talking about capsaicin. Methyl propanoic acid means it is only possible when the bond broken from here and we got this thing, and here we got a C double bond OOH. So this will only happen when we use hot, concentrated, acidified manganate. Then this would happen because in that reaction, a carbon-carbon double bond, from where there is a carbon-carbon double bond, molecule is split into two parts. So this is a methyl propanoic acid having 4 carbon atoms, right? So the reagent which makes methyl propanoic acid is hot, concentrated, acidified potassium manganate 7. Is this understandable to all of you? If any one of you has any confusion, you can ask. Okay, there are 3 different peaks in proton NMR spectrum of CH3, CH, CH3, COOH. It's a methyl propanoic acid in CDCl3. Okay. Use the table 8.1 to complete table 8.2. The typical proton chemical shift values for the protons, the splitting pattern, singlet, doublet, triplet, shown by each peak, the explanation for the splitting pattern of CH3 protons and CH proton. Okay. So let me draw the structure over here. This one, it's CH3, CH, CH3, COOH. So it means a C having a CH3 over here, a CH3 over here, an H over here, and C double bond OH over here. Now, if you see, it's a proton NMR, so the signals are of protons. If you see, these 6 hydrogens are exactly the same. And these are the alkyl hydrogen because on their neighbor carbon, there is only a carbon, only there is no other group. So these green one are actually of this type, and their chemical shift would be 0.9 to 1.7. And if you see in their neighbor carbon, this is the neighbor carbon, there is only one hydrogen. So the value of N plus 1, N is 1, so 1 plus 1 gives you 2. So it means that the splitting pattern would be doublet because the neighboring carbon has one hydrogen only. So see, the chemical shift value would be 0.9 to 1.7. Splitting pattern would be doublet as neighboring carbon has one hydrogen. Is this understandable to all of you? Now, if you look at this hydrogen, so this hydrogen is actually like this one, and its chemical shift value would be 2.0. Oh, sorry, 2.2 to 3.0. See, because this CH group has a C double bond O next to it. So see, here's the CH group has a C double bond O next to it. So the chemical shift value would be 2.2 to 3.0. Now, the splitting pattern. If you see, this carbon has this hydrogen, and on the neighbor of this, there are two carbons, and all of two carbon has total 6 hydrogens. So in this case, the splitting pattern would be multiplet. Is this understandable to all of you? So what we will write as neighboring carbon has neighboring carbons. There are two, have 6 hydrogens. Is this understandable to all of you? Just give me a minute, please. Okay. Now, this is a carboxylic acid, right? Hydrogen of the carboxylic acid. It's this one. And its signal would be 9 to 3.0. 0 hydrogen on the neighboring carbon. Or if it's bonded to an electronegative element, then in that case, there is a singlet. So here, the range is 9.0 to 13.0. And the splitting pattern would be singlet because it's not bonded to carbon, it's bonded to oxygen. Is this understandable to all of you? Okay. Now, capsaicin is heated with an excess of hot aqueous sodium hydroxide. So it means this is a hydrolysis. And in hydrolysis, amide or carboxylic acid ester bond is broken. Draw the structures of the two organic products H and K. Okay. So it would be going to broken down from here. And when it broken down from here, one structure would be CH3O. 1 minute. CH3O. A benzene ring, OH, NH2. And the other one is C double bond O. This double bond, and it's a carboxylic acid salt would produce over here because it's a alkaline hydrolysis as we have used sodium hydroxide. No, it's a doublet if there is a one hydrogen on the neighboring carbon. So 1 plus 1 gives you doublet. If two hydrogens on the neighboring carbon, then 2 plus 1, 3 gives you triplet, then quartet. And then after quartet, it's a multiplet. You have to go through the video for the NMR spectroscopy, Abdullah. Clear? Is this clear? Okay. Now they are asking, name the two types of reaction occurring in E1. So the first reaction is hydrolysis. What is the second reaction? Can anyone tell me? Yes, because it's sodium hydroxide. So basically here OH would form, but due to sodium hydroxide, a neutralization reaction occur. So hydrolysis and neutralization. Is this understandable to all of you? Yes, Soeb, did you understand this? Yes, if we use acid, then instead of sodium salt, we got a carboxylic acid. With the base, carboxylic acid is formed, but due to the presence of a base, a neutralization reaction occur and that acid turns into its salt by releasing the hydrogen and the sodium metal displaces the hydrogen. Is this clear now? And alkaline acid is nothing. Either you use a alkaline medium or use. Yeah, that's what. Okay, thank you, Sohaib. So see, that's what I have discussed earlier, that when we use this, when there is a phenol and we use sodium hydroxide, so sodium displaces this hydrogen of a phenol. So here there would be one sodium as well. Is this clear to all of you? Now, F part. Draw the structure of the organic compound L formed when capsaicin is treated with LiAlH4. So LiAlH4, if you recall, it's a reducing agent and it reduces acids and amides and ketones and aldehydes. So if you see, this is the capsaicin and here we got a amide. So that amide is going to be, uh, reduced. This remains same, phenol remains same, OCH3 remains same. And here we got NH and a C double bond O is removed. Now there is no ketone anymore. And the whole structure would be this because of reduction. Yeah, with the alkaline for if there is a uh, carbon chain on the benzene ring and that carbon that is bonded to a benzene ring, the alkyl carbon which is bonded to a benzene ring, if it has a hydrogen, then it will turn into carboxylic acid. Yes, these both reactions, this one and this one, both are the part of the AS syllabus. This one is in A2 as well, but you have studied this in AS as well. Now, question number 9A, benzoyl chloride. See, it's a benzoyl chloride. It means a benzene ring bonded to a C double bond O and that is bonded to a Cl. Can be made from ethyl benzene in a two-step process. Okay. The reaction scheme is shown. In step 2, okay, so it's very easy. Draw the intermediate organic compound M in the box. So it can be formed by carboxylic acid only. So it means here we got the carboxylic acid. See, this is the reaction which you were talking about when we use alkaline KMNO4 over here in step 1. We got benzoic acid. Okay. And that carbon which now it is easy to turn that benzoic acid into acyl chloride. So suggest the suitable reagents and conditions. So here for the reagent, for the condition, step 1, hot alkaline potassium magnate 7. And for reaction 2, you can use PCl5, or you can use SOCl2, or you can use PCl3 with heat. Now, identify the type of reaction in step 1 and step 2. So in step 1, it's an oxidation. And in step 2, it's a nucleophilic substitution. Because OH is a nucleophile which is substituted by another nucleophile, chlorine. No, how step 1 is a hydrolysis? It's a oxidation. Hydrolysis is done by a halogenoalkane, esters, amides, and nitriles. Till here, is this clear to all of you? Now, okay. C6H5COCl reacts with phenol to give an ester phenyl benzoate. An incomplete description of the mechanism of this reaction is shown in figure 9.1. Complete the mechanism in figure 9.1 and include the relevant dipoles, full electric charges on the species in the box 1 and in box 2. Okay. All relevant load pairs in box 1 and in box 2. All curly arrows to show the movement of electron pair in box 1 and box 2. The formula of the second product in box 3. Okay. So if you see, this is the mechanism that you have studied in AS only. We got a lone pair over here. If you recall, this carbon becomes partial positive, this oxygen becomes partial negative. And this oxygen is also partial negative. So from this lone pair, I'll put a one curly arrow over here and a curly arrow over here to show the bond breaking. See, now, as a result, when this happens, the oxygen which has a 3 bonds becomes a positive charge. The oxygen which has a 1 bond becomes a negatively charged. This chlorine becomes partial negative. This carbon is partial positive. So what will happen? What oxygen will do? Okay, there is no need for this. Oxygen will break the bond from here and takes the pair of electron over here. So as a result, hydrogen ion is released. At the same time, this chlorine bonds breaks the bond, and oxygen, this oxygen with its one lone pair provides the bond, makes the bond over here. So as a result, we got this. So see, H positive is removed and Cl negative is removed. So these two bonds together to form HCl. So that is the another product. This is the mechanism that we have studied in carboxylic acid derivatives. You will find that mechanism in those notes. And it is called nucleophilic substitution, or instead it is called addition elimination mechanism. Till here, is this clear to all of you? Now, see, benzoyl chloride, chlorobenzene, and chloroethane differ in their rates of hydrolysis when each compound is added separately to water. Okay, so if you recall, benzoyl chloride is a benzene with a chlorine. Chlorobenzene, no, sorry, with a C double bond O and Cl, that is a benzoyl chloride. Chlorobenzene is a benzene ring with a chlorine, and chloroethane is a C2H5 alkyl chain with a chlorine. So if you recall, the hardest to hydrolyze is a chlorobenzene, because in this chlorobenzene, that the carbon and of a benzene ring and a chlorine have a partial double bond, which makes it stronger. No, yeah, esterification is the name of the reaction. It's not the type or the mechanism. Okay, Shahan? So here I'm going to write chlorobenzene. And due to C double bond O, it's the carbonyl oxygen is the one which withdraws the bond electrons. As a result, the carbon chlorine bonds gets weaker. So this one is the one which is very easy to hydrolyze. It hydrolysis occurs at a room temperature. And chloroethane is the one whose rate of hydrolysis is intermediate between these two. Okay. So now we have to explain the reason. So in chlorobenzene, the carbon chlorine bond is strongest. So see, if I'm using the word strongest, it means I'm talking relatively that it is stronger than the others. Has partial double bond character and is difficult to break. Further, you can add over here that as one lone pair of chlorine is delocalized into benzene ring. So that's what we need to talk about chlorobenzene. Yes, it's electron withdrawing. So that's why chlorine is taking one more pair of electron with the benzene. So as a result, the partial double bond character develops and this bond becomes stronger, the strongest. Okay. Now, benzoyl chloride or in benzoyl chloride, carbon chlorine bond is weakest because of C double bond O withdraws electrons. Now last in chloroethane, alkyl has positive inductive effect. So due to the positive inductive effect, it becomes relatively stronger than carbon chlorine bond than benzoyl chloride because where the electrons are getting withdrawn. And but in chloroethane carbon chlorine bond is weaker than chlorobenzene because in chlorobenzene one lone pair of chlorine is also delocalized. So till here is this clear to all of you? So here we have completed this paper, and in tomorrow's class that will be probably starting at 9:30 the same time. We will be starting the February March 2024. Okay. So see you everyone in the next class. Take care. Okay. Allah Hafiz.